Hey, great question again here. Thank you. I've drawn our original vector here, and that's got a component that is a directional vector and a position vector. For part A, if we're looking for something that's parallel to the original line, because this is representing a line, it's got to have the same position vector. And if it's an equation of a line, well, it's also got to be this r vector. All it's going to have is a different position vector, and that position vector is just some point on the line L. And because we know that it passes through this point A, that just is our position vector. So we can just write as 1, 3, 2 plus t, and then our direction vector. And then what that would look like is if we've got something in 3 dimensions here. If you've got our original line like that, say, the other line might be down here, but it's still going to have that parallel shape to it. Yeah. Oh, and I should also mention, I like to write my vectors as column vectors. It just makes more sense to me. For instance, I can see here that the k component of the direction vector is 0. I also just think it's cleaner and a bit quicker to write, but that's why they look like this and not in I and J's, but they're equivalent completely. The other thing to mention actually is that this t value can probably become some other constant such as k. It doesn't really matter. It can be k, it can be d, it can be quite a few things, but it's just some scalar multiple of that same direction. All right, and then the nuance here for part B comes from the property that if we find the scalar product of two vectors, or the dot product, that are perpendicular, that'll equal 0. And so we can use this property here, like the actual point of intersection is still given to us as A. But what's different is we now need to find something that's perpendicular to line L. And we'll just start with that. We can tackle what the parallel to the xy plane means after. So if it's perpendicular to line L, it means that, obviously it's got that kind of shape to it. But all that means in reality is that the direction vector of L, which is -1, -3, 0, dotted with our unknown direction vector here. So I'm just going to call that D1, D2, and we can say D3, is going to have to equal 0. All right, here's where we can bring in the parallel to the xy plane bit. So this isn't necessarily like crucial, but because we're working in 3 planes, you could argue that, okay, well, you've got multiple perpendicular vectors. Like, yes, it can be perpendicular on the actual plane that we're looking at, but it could also be tilted a bit that way and still be perpendicular in 2 of the planes. And so for that reason, what the parallel to the xy component bit means is that we're not actually increasing our elevation in the z plane. In other words, our directional vector doesn't have a k component. There's no rise. It's just staying flat on the xy plane, not going up into 3 dimensions. And so that means that this is actually going to be a 0, and we can pre-fill that. Okay, so onto our scalar multiple here. So we know that that will move to -1 times d1 plus -3 times d2, and that is to equal 0. If we rearrange this, we can move our -3 to the other side. So therefore we got -d1 equals +3 d2. And what I actually like to do here is just get a bit of a ratio, in fact, of d1 to d2, because you've got to remember that a direction vector can be scaled down or up based on our scalar multiple. So as long as the 2 values are in proportion to each other, it doesn't particularly matter. We can just express them as the lowest possible ratio. What I mean by this is that if we say divide both sides by -1, so we get rid of this -1 over here, that will then give us d1 equals -3 d2. We can then divide both sides by d2. And that will give us a ratio of, okay, the ratio of d1 to d2 has to be -3. And the simplest way we can accomplish that is by saying that that means the direction vector, so the implication is that the direction vector D has to equal something in the ratio of negative 3i, 1j, and 0k. And so that's what we can come up with there. There are other alternatives of that, like as long as they're in, like if we could have positive 3 and negative 1, same thing, because remember, when we go back to our actual solution here, and we're talking about, okay, what does the resultant vector equal? This vector of a line, it passes through that same point, so 1, 3, 2. But remember in here, we've got this scalar, and so it doesn't particularly matter if this was negative 6 and 2, as opposed to negative 3 and negative 1, 0. It just means the k value will be slightly different. So what's important is the direction and the actual trajectory of the vector. And yeah, so that's what I would have for both of those. My drawing isn't great here, but yeah. All this parallel to the xy plane bit means is that the k component of the direction vector is 0. And then perpendicular utilizes our scalar product condition, and the first question is just substituting in a point that we know is on the line. Hope that's helpful. Any questions, you can just let me know in the comments. And yeah, if you're enjoying it, please consider subscribing. That'd be great. And yeah.